All right, so today what we're going to do is just look at a new cycle, but it's not new material. It's just using the material we have learned. We just do like an application, but it's nothing new. So we're going to look at the refrigeration cycle. And here, basically, let us do a review over here. A very quick review of what could be a refrigeration cycle. Okay, so by definition, we did study that every single system needed to have a hot reservoir. So every thermodynamic system is operating between a hot and a cold reservoir. So if our system here is, this is our system. There's actually two ways to cool a system. All right, so what would be those two ways to cool a system? So both of them would be to do what is either you can remove heat from the system into the hot reservoir, or you could put cold into the system, okay? But what is something that happens in both cases is that in both cases, you need to provide work or power, okay? So if you remember when we did this one, we say here is like two different parts. You can look at it like, if you look at the bottom part, this would be what is known as a refrigeration system. And then if we have to look at the top, what would that be? A heat pump system, okay? So nowadays, when you're gonna install your cooling system in the house, sometimes you're gonna see some of the machine are heat pump, some of the other one are refrigerations, no? Okay, so I don't really recall what were the variables that we were using. I think for the refrigeration was beta, but I remember for the heat pump. So let's just look, since we're gonna do the refrigeration, we could do the heat pump as well. So let's say here, let us look, or let us analyze the refrigeration system. So if we analyze the refrigeration system, what should be the efficiency? If you remember, the efficiency is always whatever you put in or get out. I mean, what are you trying to achieve? Divided by whatever you need to put into the system. So what are we trying to achieve over here? To put cold into the system. And in order to do that, what do we need to do? Put work or power, okay? This equation would work even if we put points or no points, okay? But if you want here, let's put the points because it would be more related to the power. So put the points everywhere. But it's the same thing with just, the reason I'm putting the points is because a refrigeration system is really an open system or a control volume system. So it will make more sense, okay? Okay, so if you want here, maybe we can do this. This is not the way we'll solve it later on, but okay, so really this should be equal to what? Should be equal to Q in divided by what? It should be the absolute value of this one, no? The Q in minus Q out. And if we remember, we said that for an ideal case, you could say this will be equal to what? T cold over T hot minus T cold. But okay, so all this stuff, again, this is none of the book, it's me who's trying to explain to you how is the refrigeration system. So this is what we get from just the theory, all right? So now, into the more practical case, how is a refrigeration system model? So generally you will have here a condenser. That will be attached to a compressor. Okay, then see, I'm gonna do this. So if we come here, then here we're gonna have a or an evaporator. And then again here now, in here we're gonna have a valve. So let's see, I think this is the symbol gonna use. So this is a compressor. This is a valve. So basically what I'm trying to say is that all this over here is your system. So if we compare to this one, what should we have over here? We should have over here, where the function of the evaporator is going to be to have some Q in. This will be your cold reservoir. And this would be here your Q out. Where this will be your hot reservoir. And now, what is the component that requires work or power? Will be the compressor. Okay, but basically what I want you to realize is that this figure is identical to this. What happened here is that now the system here, the box, this is what is supposed to be on that box. Okay, so this is for the refrigeration. Obviously this system will be a bit different if we had to deal with the heat pump. Okay, but here we're dealing with the refrigeration system. Okay, so if we have here this notation, I'm gonna put numbers and then I'm gonna do a little figure. So this should be 1. Then if the compressor is ideal, what does that mean? That it's gonna work isentropically, no? So we can say this will be 2 isentropic. What we have been calling 2s. And then everything remains unchanged, it will be 3. And this will be 4 over here. So I wish I had some space to do it over here, but it's going to be too little. So what is the general form of a refrigeration cycle? So if we do the figure, on a TS diagram, okay? So again, let's see if I have space to keep both figures together here. Okay, so what is the function of the evaporator? What's gonna happen to the evaporator? You're gonna go from, you have something hot, which is gonna become cooler, no? Yeah, so where should we be on this line over here? So let's say we start from somewhere over here. This will be our location 1. So this is 1 over here. You go through the evaporator now. What's gonna happen? We're gonna move in an isentropic form. So that means S1 equal to S2. So we should move along a line over here. Okay. S1 equal to S2. This is an isentropic. And let's say we get to a point that is over here, 2S. We go from 1 to 2S. So I'm starting from here, sorry, I'm starting from this point. The evaporator will come at the end. So it's when you cool over here. So we come here. So when we hit it, this will be the so we get it here to this point here too. Now we go through the condenser. So what are we doing? We are cooling, no? Okay, at constant pressure. So if you remember, this will have lines of constant pressures. We could say we go here through the line of constant pressure. Then let's say we have a gas, it's going to become a mixture. And this should be 0.3 over here. All right, and now this is, I just put it down, is that you will have now, you will come over here. And 0.4 will be over there. Okay, and if you want to think about it, this line over here is our T hot, and this line right here is our T cold.
Why is the process from 3 to 4 not straight down?
Because that's generally the way it is for the solution system. It could be because 3 to 4 is a valve, so valve you always lose.
Okay.
It's not isentropic, okay?
Okay.
All right. It's not like a pump and a valve is losing no matter what. That's why it's basically moving. The entropy is increasing. Okay, yeah. That's the reason. Okay, so this is a general shape. So now, if we needed to look at the relation of so let's see. So we look at this figure and compare to this one. what should be Q in? Q in should be equal to the mass flow of what? H1 minus H4, no? This is like we have the cold system that represents, we look at this figure, Q in H1 minus H4, okay? And then what should be the one of the, what I'm trying to do is write an expression for this. Now, what should be the value of the power? The power will be related to the 1 and 2, no? And the power should be related to what? So let's see. H2 minus H1. All right, so that the expression for the efficiency that we had, beta equal to Q in over the power, will simplify to what? H1 minus H4 divided by H2 minus H1. Okay, so this will be the efficiency of refrigeration cycle. Okay, so basically you see, this is what, now when solving the problem, so let's see what problem we solve. What we'll have to do is to find what? H1, H2, H3. In this case, what do we have? In here, in this problem, we are assuming that the refrigeration system is ideal because the compressor is working isentropically. But in real life, what should be this line? This line should not be either straight, should be coming a bit to the right, no? Okay, so that might be the next problem we do, but let's first do on the ideal case. Okay, so over here, if you want, since you asked the question before, let me put it here. S4 is a little bit to the right of S3 because valve always loses energy. Meaning what? That the entropy increases. If you remember, what is a good definition for entropy? Is a measure of how well you use the energy. If you don't lose any energy, the entropy will be zero. But if you waste some energy, the entropy will become positive, no? Okay, that's the definition. Okay, so this is one example. I took this one from the textbook, so I have the solution for once. So let's say, so example should be a direct application. Okay, and if you want to know, this is in page 614 of the 8th edition, okay? Of Moran and Shapiro, if you want to look at it. Okay, so basically it's exactly what we just did, but just put in value. So they do a small figure over here. So let me show it to you. That way it will be just easier since I took it. So this is a problem that I printed before. So let's try if I can zoom in a little bit so we can read it. And then we can do the figure. So basically, this system is not exactly the same, but this is kind of similar to what you have in the cars. All right. But anyway, refrigerant 134A is the working fluid in an ideal vapor compression refrigeration cycle. So ideal, why? Because this works isentropically. Okay. That communicates thermally with the cold region at 0 degrees. So this here looks like this a cold region here at 0 degrees, and the whole reservoir is at 26. Saturated vapor, so 1, saturated vapor here at 1, enters saturated vapor enters the compressor at 0 degrees Celsius, and saturated liquid leaves the condenser at 26. So saturated vapor, saturated liquid. Okay, those two locations are here. The mass flow rate of the refrigerant is 0.08 kilograms per second. Determine the compressor power. So how much power is required? The refrigeration capacity in tons. I don't know what that is, so we'll figure it out. And the coefficient of performance. Okay, the coefficient of performance of a Carnot refrigeration cycle operating between the warm and cold regions at 26 respectively. Okay, yeah, I can do that. Part B is the only one that I'm not sure exactly what they're asking for. So let's do the figure. So how can we do 2 feet? Okay, so so on top we're gonna have the condenser. At the bottom we have the evaporator. On this side we're gonna have the valve. So it's the same as before. And on this side, I do everything a bit smaller so I can fit. We have the compressor. Again, we know this is 0.1, 2S, 3, 4. So this is Q out. This is Q in. Okay, here is the hot reservoir. Here is the cold reservoir. So basically, if I do the figure of the cycle, this figure is extremely important. This one here. We have the TS. Same figure as before, but we do in this case. So we go from a line of constant. So we go from 1 isentropically to 1 to 2 or 2S. From here, we go through a line of constant pressure. In this figure, they call this point here A. So this is now three over here. So this is what's happening through the condenser, okay? From here to here, whatever happens to the condenser. So we go 1, we compress isentropically to the compressor, we go through the condenser, so we're cooling down. Now we go through the valve, so we know if it was an ideal valve, it will be isentropic, but we know we're gonna lose some power, so 4 goes somewhere to the right. And then on the evaporator, again, this part will be heated this way. Okay. And in that figure, maybe we can add it. What is the hot temperature? They say it was 26 degrees Celsius. So, okay, so let's put on Celsius, 26 degrees Celsius. And the T cold over here is 0 degrees. Okay. So if you want, you can put it here. I wasn't going to put it because I don't want to do too much. I don't want to put too much, but if you want to put everything here, what should have the cold reservoir at T equals, so T cold equals 0 degrees Celsius. And this one here should be the hot reservoir at T hot 26 degrees Celsius. Okay, but generally I don't like to put all that information. Okay, so the first thing we need to do is what? To determine the compressor power in kilowatts. So we need to find, didn't put the figure here, the power required to run the compressor. Okay, we just over here the, okay, I mean, you see, you don't need to know the equations, but what should be the equation to run the compressor? H2 minus H1. Really, it should be H2S minus H1, no? Okay, but if you want, following the procedure to find the power, what do we need to do? Take the compressor as our control volume. Okay, so let's just start from 0, let's say. So we don't know the equation, so let's say here, that way, that will be a review of the procedure. So let's say part A, we need to find the power. So what we need to do here is just to consider the compressor as our control volume. So this is our compressor, so this will become our control volume. We know this requires power, and that this is located between 1 and 2S. Okay, release 2S. So if we apply the principle, the first principle of thermodynamics to this system, what do we get? Heat transfer minus power plus what? M H1 equal to M H2S. So in this problem, what do we know? Do we have any loss of heat through the compressor? Do you see that on the figure? So this is 0. So from the figure, we find that the power should be equal to what? M dot H1 minus H2S. Okay. So in the problem, I forgot to put it. Let's see what it is. But basically, the mass flow was given to us, and they said that the mass flow, so the mass flow M dot is equal to 0.08 kilograms second. All right, so we need to find basically H1 and H2. So how do we find H1? We go to the tables now, and we need to know two things. So what do we know? I mean, we know saturated vapor, and what else do we know? The temperature. Okay, so we know two things. We can go to the tables. So let's see what is that table.
So we know the refrigerant is like the name of refrigerant, right?
Refrigerant 134, yes. So let's go to the tables. Let me pause as I go to the tables. So we go to the textbook, we go to the table 810, which is a property of the saturated refrigerant 134A. So we know two things. We know the temperature, and we know that it is saturated gas. So we need to go here and look at what? H sub G, that column here. So that will be 247.23. So I put here, table 810. Putting this on the notes. At saturated gas or vapor and T equal to 0 degrees Celsius, we find that H1 is equal to 247.23 kilojoules per kilogram. Okay, basically that's what the only thing I do over here. So we found H1 over here. Now we need to find H2S. So how can we find H2S? We need to know two things. So what do we know? We know the entropy, no? S1 should be equal to S2, but what else do we need to know? Do we know the temperature? No, because this is 26. But what do we know? What happens between here and here?
Constant pressure.
This is constant pressure. So what we can do is maybe go to the tables, find out what is this line of pressure for these 26 degrees. The 26 degrees would be the temperature over here to find out what is the pressure, no? Okay. So hopefully we have it here on the tables. So what should be the pressure? If we are lucky, yeah, we're lucky. So what is that pressure? If you go from table 810, the pressure is 6.8530. Okay. So let's write over here. I'm going to a table here. So this is for H1. Now we're trying to find H2S. So we know that line of constant pressure. So constant pressure. So we know that from table 810, at T equal 26 degrees Celsius, the pressure is 6.853 bar. Okay, and that's what I show here on this page over here. Okay, what else do we know? We know that this is isentropic. Okay, we go through the line over here. All right, so we know S2. Oh, so we have to find S1. S2 equal to S1. So maybe we need to go to the tables and S1 here. So we need to be careful here. Okay, so S1 here will be equal to what? S sub G. So let's come over here. So we need to go now to the 0 again. And what would be S sub G is that value here, 0.919. So the 0.919. Okay, so S2 equal to 0.919. And the units for this one should be what? Let me just put on the first one, kilojoules divided by kilogram Kelvin. So from the figure here, what do we know? What is the state of this one? Oops. What is the state as state 2? It's superheated, no? So we probably need to go to the superheated tables. Okay, and what else do we know? We know the pressure and we know the entropy. Okay. All right, so over here we know two things. For H2S, the two things we know are what? The pressure is 6.853 and the entropy is 0.919. Okay, so as I was explaining outside the recording is that when you go to the textbook table A11, I'm guessing, no, A12, this is the superheated tables for the gas. Obviously, they're not going to have a table for the pressure of 6.853. So that means that we need to do what? Interpolate between these two tables, okay? So we need to interpolate between those two tables for what? For the enthalpy, which would be this column, and the entropy. So let's rewrite this value, and I'm guessing this value, and this value, and those four values for each one of the pressure. So which is what I'm going to be doing now on the page. So P equals 6, P equals 7. I'm going to write H equal to 259.19, S equal to 0.9097, H equal to 261.85, S equal to 0.9197. So this is basically what I wrote on the page. So that now we have the information needed to interpolate. Okay, guys, sorry for that. We need to add another set of data. They're not going to be in order, but so basically for the first one, for 6, we took the 259. We would have to take now the H equal to 267.89 and the S equal to 0.9388. And now the other one is going to be reversed. Sorry for that. We need the H for the first one, which is, oh no, we took the first one, so we're good. We need the H for the 265.37 and the, oh, but I did a mistake here then. The previous S was 0.908, so you will see on the correction, and this one would be 0.9197. So let's see. So this is the data that I have. So we need to interpolate a lot. So let's do it. And let's see what we get. Okay, so interpolating. So what do we need to find? We need to find our pressure that we are interested in is 6.853. So we're gonna have to interpolate multiple times doing what? We need to find what we're trying to solve, what we're trying to find. We always put it on the y-axis, and what we know, we put it on the x-axis, no? So basically you can see you can have here the pressure 6, pressure 7. And I'm going to try to find the H and the S's. So hopefully, yeah, we should work. That should work. Okay, so basically what should we have? So let's try to solve then at this pressure here. Let's solve here for H sub A will be equal to what? Will be equal to, so if I start by the H, will be equal to what? 259. I'll do the first one, I'll let you do the other ones. 259.19 plus the slope, that will be 261.85 minus 259.19 divided by 7 minus 1 times what? 6.853 minus 6. So if you do this calculation, what do you get? Yeah, good correction here is 7 minus 6. I was just thinking about one. It's 7 minus 6, okay, over here. So again, we do this one together, but then you need to do the same thing for HB, S sub A, S sub B, no? Okay, so basically this is the data. This one we did it together in class. This one you did on your own, so I hope it's correct. So now we go here from, so we go from A to B again. And now what is the value that we know? So we know the S's, but we need to find the H. And the S that we know here is the 0.919. So we're gonna have H2S, which is what we're trying to find, should be equal to what? H sub A plus H sub B minus H sub A divided by S sub B minus S sub A times the 0.919 minus S sub A, S sub A. And this should give us the value for H2S. So guys, so basically now we have all the information because we did all this stuff for what? To substitute into the equation for the power, okay? So we can solve it here that the power required to run the compressor, okay, we know it's power equal to mass flow of H1 minus H2S. So if we do the numerical application, we get that the power is equal to 0.08 kilograms per second times H1. We found H1 to be 247.23. Let's say, oh yeah, 247.23 minus H2S 264.58, and this is kilojoules per kilogram, but the units in watts. So what is a watt? Is a joule per second, no? So we want kilowatts. So 1 kilojoule per second, no? Okay. So please go ahead and do this calculation.
I got a negative.
Number as well.
Okay.
Well,
That is fine.
makes sense because-
That is fine because of sign convention.
1.38 we're powering the.
So what do you get? We should get here, they get about 1.4. We're gonna get 1.3 something.
1.38 or 1.39 if you round.
Okay, 1.39 kilowatts. So the reason of the negative value here, really we should have, is because on the textbook convention is what? Is we had that the
Work done.
once the work done by the system is positive and the work done on the system is negative, no? So since we need to provide work into the compressor, we get a negative value. All right. So part B, they were asking you to find the, which I did not understand, but now looking at the solution, it's very simple, the refrigeration capacity in tons. So basically what that is, all we need to find is what is Q in. Okay. So what would be Q in? We are over here would be, we can look at the figure, will be H1 minus H4. Okay. So Q in will be M dot H1 minus H4. And now from the figure, we already know what is H1. So that's a good thing. So H1, we found that to be 247.23. But we're gonna have to find H4. Okay, so now we need to look at the figure. So we have 3 and 4. Okay, so let's first go and find 3 very quick. Okay, we can find 3 because we know it's saturated liquid. Okay, and we know the temperature. So let's say H3, we know is saturated liquid, and we know is at T equal to 26 degrees Celsius. So I guess we can go to table A10 at T equal 26 degrees Celsius, and from here we can read H3 will be equal to H fluid or HL. I don't remember which one they use. And what would that be? So table A26. Sorry, A10 at 26. Here we go. We look for H fluid, no? Which is 85.75. Okay, and now, you remember, you could do it as well, but I'm going to be quick. Now, what do you know about the valve? They don't lose, the enthalpy is the same, no? Let me do it very quick, okay? And now, so between 3 and 4, we go through the valve, okay? I did that, I already told you, but let's say you do the valve over here. And let's say this will be your control volume. So if you apply the first principle of thermodynamics, what do you have? Q minus power plus M let's see, what would that be? 3, 4, no? Plus mH3 will be equal to mH4. There is no heat or power. So I told you that through a valve, the value of the enthalpy is conserved. Okay? So at the end, what do we have? So that H4 equal to 85.75. And now we can find that Q in. We do the numerical application equal to m dot H1 minus H4. So I'll just put the values because we know we're running out of time. They ask you to find this in tons. So this will be equal to 0.08 kilograms per second times the 60 seconds in a minute. We find out why they do that in a second. Then we have H1 is 247.23 minus 85.75. This is kilojoules per kilogram. And the last unit transformation is 1 ton is equal to 211 kilojoules per minute. So maybe you can punch the numbers, but I'm guessing, I'm going to put the result here they give you is 3.67. Let's say for us, it's going to be 3.66. But do the calculation, okay? So in this case, we'll have here.
What does that say? 1 ton of what?
211 kilojoules per minute. Okay, and this should give you that Q in tons. Again, if you want, run the calculation, but I'm going to try to gives you that Q in is approximately 3.66 tons. Okay, and when you go and buy, or if you want, you can go and check the refrigeration machine of your house. Probably they will give you the tons as well as the coefficient of performance. So let's do it very quick. You don't copy here, but let's run. The beta we say was equal to what? Q in over the power. So we say was equal to H1 minus H4 divided by H2S minus H1. If you do the calculation, you get about 9.2. Okay, that way we are done with the problem. So now if you want, if you are curious, go and check your refrigeration machines, probably located in the garage or in the closet. And probably the numbers you're going to find out is this one, the coefficient of performance, 9.2. And also, so this will be the performance of the machine. And then the amount of cold that you need to put into the house, depending on the size of the house, will depend on the number of tons. So we have machines, I don't know, will be maybe 2 tons. Some of them will be 4 tons. Some of them will be 6 tons, no? So this defines the performance. This defines the size of the machine that you need for your design, the refrigeration system of the house, let's say. Okay, sorry for those 3 minutes. I'll give you those 3 minutes next time.
Give them thoughts on the test.